Good morning, everyone. My name is Danoglidis, Assistant Professor of Research at the University of Texas at Arlington. And today I will present you our research about the multiscale characterization and modeling of electron kinetics in concrete, which is engineered with carbon-based nanomaterials. And this work was accomplished by Professor Maria Konstanthoutos and our PhD student Rohitasva Kumarasinghe. So, I will start the presentation by giving you a brief introduction about the electrical properties of concrete, and actually of nano-engineered concrete, of concrete reinforced with conducting nanomaterials, for example, carbon nanotubes or carbon nanofibers, all right? And here you see a transition from the nanoscale to microscale. And actually, I want to start from the microscale here. We all know that a concrete reinforced with carbon-based nanomaterials, carbon nanotubes and nanofibers exhibits a high electrical conductivity. All right, we are talking for an electrically conducting concrete. Here also I included a Nyquist plot. A Nyquist plot shows us the electrical behavior of these concrete nanocomposites. And actually we have the horizontal axis, the electrical resistance that we use to determine the electrical conductivity of the material, but also in the vertical axis we see the reactance, which represents the ability of the material to store electrical energy. And here actually we see a pattern which is more complex than a linear behavior of electrical conductivity and reactance. Actually, we expect that once the electrical conductivity increases, that the electrical resistivity decreases, we expect a lower reactance values because the material, the electron kinetics in the materials are increased, are high, the electrical current is facilitated, and we expect a linear, let's say, proportionality between the two parameters. However, we see three arcs here. So the behavior of the concrete nanocomposite, the electrical behavior, is much more complex than what we expect. And actually, we talk about the electrical conductivity and dielectric permittivity. These are two true material properties that we use to any material, and especially nanocomposite materials, to characterize the electrical behavior and the electrical energy storage capacity. And these two are relied at the nanoscale. We are talking for the formation of a conducting network of continuously interconnected conducting nanomaterials. Again, for example, carbon nanotubes. And when we talk about the nanoscale, there are two parameters, two critical parameters that we need to evaluate, to study. The tunneling distance, which is the tunneling of electrons from the interconnected nanomaterials, and the energy density, which is the concentration of electrons available for electrical conduction. And I will walk you through this in my presentation. So for this presentation, we prepared 28 days mortar nanocomposites reinforced with carbon nanotubes at a range of 0.05 to 0.3% per weight of cement. And we conducted AFM, tunneling AFM, electrical current mapping, and nanoscale topographical imaging in these samples. So to measure the tunneling distance and electron density, and then to form some equations, if I may say, more similar, to calculate the electrical conductivity and dielectric permittivity. Again, these are two true material properties. So here in this slide we see a typical AFM topographical imaging and current mapping at a 5 nanoscale. And essentially what we see here, we see the interface between the calcium silicate hydrates and the conducting nanomaterials. And how can we distinguish this from the current mapping? Actually, the black area, the shaded area, represents the calcium silicate hydrates, while the lightest area is the conducting nanomaterial. And here, in the current mapping, we see the range of the current that we measured. We are talking for very low ranges, attoampere and picoampere. So we measured the current actually at an ultra low level from atto to pico. Before we start with these AFM results, just to introduce the actual experimental values of electrical resistivity that we published about these mortars, 28-day mortars, AC measurements, reinforced with the carbon nanotubes from very low amounts and up to 0.5% per weight of cement. And here we see actually a degrees of the electrical conductivity as the nanotube network is formed, up to an amount around 0.1 to 0.2 when the resistivity reaches a plateau. And seems independent of the carbon nanotube content, and this is actually the percolation threshold. In our previous research, we evaluated, we studied, we examined actually two different mechanisms here. One, the electron hopping, when the electrons, it is the mechanism for the transfer of electrons when the network of nanotubes is non-continuous, and the electron tunneling when we form a continuous network of nanotubes, and the electrons can very easily pass the nanocomposite. So in this slide, I will start with the AFM imaging of a plain mortar. And actually, here we didn't use conducting nanotubes, and we see in the left part of this slide, this current mapping, and actually we do not get any signal. We just have a black background with some white spots, probably due to the porosity of the material. And we also see a very, very low range from the attoampere, from 3 to 6. That means that the material is an insulator. It's not a conductive material. And indeed, from the experimental results from the microscale, from the Nyquist plot here, we calculated a very low electrical conductivity of 1.1 Siemens per meter. Then here is the AFM image of the mortar reinforced with carbon nanotubes at a low amount of 0.05% per weight of cement. And we see the formation of some nanotubes. How can we distinguish this again? The black background is based on the cement hydration products, no signal, while the light colors area are our nanotubes. And we see that the range from the current mapping, from attoampere, we go some orders of magnitude higher to this picoampere. Now, if we will measure the distances between these light color spots, we see some distances, for example, 173.7, 124.3, 189.2. So This is actually the tunneling distance. We are able to measure the tunneling distance that shows us the electron hopping mechanism of the charge of current from nanotube to nanotube. So, using actually our tunneling AFM, the software of this AFM, we were able to map the area, so to get these tunneling distance values of our mortar nanocomposites. Here actually we see a typical probability tunneling distance plot, very similar to the plot that we obtain for the modulus results from an AFM, from a typical AFM. 400 readings, we follow the Gaussian fit curve, and from the results we found that a mean tunneling distance for this particular sample, mortar reinforced with nanotubes 0.05%, is 132.2 nanometer, far away from this threshold. The threshold 80 to 70 nanometer is the tunneling distance threshold, so we can consider a material with a continuous network within the matrix. We increased the content of nanotubes from 0.05 to 0.1% per weight of cement, and in the right part of this slide we see the AFM of this sample. We can identify a more dense light color areas in this image, and also the distances between these light color areas, the tunneling distance, is much lower, 67.3 nanometer, and also we see the range of the current mapping. So now, if we will summarize the results for mortars with the nanotubes from 0.25 and up to 0.1% per weight of cement, we see a consistent decrease of the tunneling distance from this large value of 170 nanometer to 67 nanometer. Indeed, this value, the tunneling distance for the 0.1 CNT mortars, is lower than the threshold that is defined in the literature, 80 to 70 nanometer. So, from these nanoscale experiments, we can obtain that this amount, 0.1% per weight of cement, is critical for the formation of a electrical network that is continuous and facilitates the electron transport. From the analytical calculation, we see a proportionality here with the electrical conductivity. Actually, we calculated the electrical conductivity, and we see that once the tunneling distance decreases, the electrical conductivity increases from 1.3 to 2.2 Siemens per meter, 70% higher, using 0.1 nanotubes. And we see that the calculations are in good agreement with the experimental measurements, the AC measurements here. We increased the amount of nanotubes from 0.1 to 0.15% per weight of cement, and here we see the current mapping AFM image, and we see continuous networks of nanotubes within the matrix. Here I included a relationship between the tunneling distance and the electrical conductivity. And what it is clear from these results is that the electrical distance decreases up to 0.15 from 170 to 46, and then reaches a plateau at a value of around 45 nanometers. And so, from the calculations, as expected, the electrical conductivity increases from 1.3 to 2.5 Siemens per meter, and then reaches a plateau and it is independent from the carbon nanotube content. So from the electrochemical impedance spectroscopy and the theory, we know that once the electrical conductivity reaches a plateau, then we talk about the percolation threshold. And we can assume that the percolation threshold for this particular type of nanotubes is between 0.1 to 0.15% per weight of cement. So our theory, previous theory, for electron hopping mechanism for non-continuous CNT networks and the electron tunneling for continuous CNT networks can be visualized now with this nanoscale imaging and the results. And that was the first part of this presentation about the electrical conductivity of the nanocomposites. But I also mentioned about the electrical energy storage capacity of the material. The electrical energy storage capacity, which is a dielectric permittivity, and I will show you the results, relies on this electron density. What is the electron density? Refers to the concentration, the actual concentrations of electrons that are available in the matrix for electrical conduction, and actually is a measure which is inversely proportional to the storage of electrical energy. So here we see the change in current density to change in voltage of these mortars reinforced with nanotubes from 0.025 and up to 0.1. And we see that once we establish a continuous network within the matrix, this current density changes, increases by 500%. Meaning that the material is able to release the electrons, is not able to store energy. So this increases, transforms the insulating behavior of the material into a conducting material. And in this slide, I'm showing you the results, the current density results of mortars reinforced with nanotubes for amounts higher than 0.1% per weight of cement. And I showed you previously that once we reach the percolation threshold, the electrical conductivity is high and it is independent on the nanotube content. However, here this is not the case for the current density. And actually we see that increasing the amount of nanotubes, the current density decreases, and decreases up to 300 and 350%. And this indicates that the material is able to store electrical energy. This is represented by the true material property, the dielectric permittivity, and here we see the results from the calculations. From the dielectric permittivity decreases, the material is able to release electrical energy up to 0.1 when reaches the lowest value, and then proportionally decreases. So what is the mechanism of this? We talk about the conducting material, how the electrical energy is stored here. And for the last part of this presentation, I would like to introduce a study about the nanoscale, the electrical properties at the interfaces of the nanocomposites. And here we see the AFM from an individual nanotube, mortar in an individual nanotube, 0.1% per weight of cement. We were able to scale down to 5 nanometer, so to measure the mapping, the current mapping, for a CNF, interface, and CSH. And actually, we talk about the interface. We measured in 1 nanometer spots using this tunneling AFM the current density and the change in voltage for these 0.1 CNT mortars. And here we see the response of this interface, of this red colored spot. And from this current density, we were able to calculate a dielectric permittivity of 8.2 farad times centimeter. Now, we also measure the interface, electrical current, and the interface between the CNT and CSH in mortar with 0.15% per weight of cement, this 1 nanometer spot. And we see a decrease in the electron density of the material, 4 times lower. That means that the electrons are stored within the interface between the nanotubes and mortars. And for this is the agglomeration state of the nanotubes for amounts higher than percolation threshold that leads to a higher storage of electron within this interface. And as a result, the dielectric permittivity of this interface is much higher, 21.3 farad times centimeter. So, to conclude, we can use the tunneling AFM as a tool to identify the 2 nanoscale properties, tunneling distance and electron density, which are related with the electron kinetics in nanocomposite materials. We use actually these 2 properties to evaluate the bulk electrical conductivity and dielectric permittivity, and from the results we found that the 0.1 is critical of nanotubes, is an amount critical to establish a continuous network within the cementitious matrix. So we reduce the tunneling distance for higher electrical conductivity and increase the electron density for a lower dielectric permittivity. I would like to acknowledge our NSF PIRE project with Professor Sobolev for this research, and thank you very much for your attention.